Hello everyone, welcome to SCI-EASE. In this video, I am going to discuss a very important topic, that is Pauli Exclusion Principle. In continuation to off-bow principle, which we have already done, two rules, Pauli Exclusion Principle and Hund rule, they are very important for filling of the electrons in the orbitals. The electrons, they are filled in the orbitals, they are restricted by exclusion principle. And this principle that is given by Austrian scientist in 1926, and the name of the scientist is Wolfgang Pauli. What this principle states: no two electrons in an atom, each and every word is very important. No two electrons in an atom can have the same set of 4 quantum numbers. Can have the same set of 4 quantum numbers. You know that there are 4 quantum numbers. First is principal quantum number denoted by N. Then is azimuthal quantum number denoted by L. Then is magnetic orbital quantum number denoted by ML, and last one is spin orbital quantum number denoted by MS. So from this definition, this first definition, what we conclude that 3 quantum numbers, they may be same, but 4th quantum number, that will be different for the electrons. Okay, so here I will take one example, the things will become more clear. Another definition of this Pauli exclusion principle is only 2 electrons may exist in the same orbital, and these electrons must have the opposite spin. Okay? Only the 2 electrons that can be accommodated in one orbital, and those out of those 2 electrons, their spin that is opposite. One electron will be having spin up, and another that will be having spin down. Okay, so here I will tell you the you know that subshell 1s, subshell 1s, it is having only one orbital. It's having only one orbital. Okay, so this is 1s, and how many electrons that can be accommodated? 2, one with spin up and another will be spin down. Now 2s, come to 2s. It's again having, this subshell will be having again one orbital, and it will have again maximum of the 2 electrons. Now come to p orbital. Come to p orbital, 2p orbital. This subshell will be having 3 orbital, and the maximum, it can have 1 electron, it can have 2, it can have 3, 4, 5. But the maximum number of electrons which can be accommodated in p subshell, that will be 6. And like this, one with spin up and one with spin down. Now take the case of d orbital, d subshell. D subshell will be having 5 orbitals, and the maximum number of the electrons, which can be here 6 electrons, they will be accommodated. Maximum 10 electrons, they will be accommodated in d orbital. Okay, so this is maximum. It can have 5, it can have 2, half filled, fully filled, or like this. It will be having how many? And so on. And if we take the case of F, this subshell will be having 7 orbitals and the maximum 14 electrons that can be accommodated, and so on. Now here I want to tell you this, according to this definition, that no 2 electrons in an atom can have the same set of 4 quantum numbers. Here I will take the case of magnesium. Magnesium with atomic number 12. Here we write the atomic number. According to Aufbau principle, its electronic configuration will be 1s2, 2s2, 2p6 and 3s2. Okay. Now, here 2 electrons, they will be accommodated here. 2 will be here. Then you take this 2p, 6 electrons, they will be accommodated. And now you take the case of this 3s, it will be having 2 electrons. Now I want to tell you one thing. Here I will take the case of the electron which is having spin up. And here 3s. Okay. And here I am taking the case of the electron which has spin down. For this electron, you know that n, that will be equal to 3, L, 0, M, 0, okay, ml. And S, what is the spin? It is spin up, so it will be having plus half value. Okay. Now, take the case of this electron. What is its result? Can you tell? Here again n, that is equal to 3, L, 0, M, 0. But what is the value of S? It is minus half. So, what you have seen here, that the 3 quantum numbers, they are same, but the 4th quantum number, that is different. You can take the case of any element and write its configuration, and you will see that no 2 electrons in an atom can have the same set of 4 quantum numbers. You can take as many examples as you can. Now, from all this discussion, what we have concluded? We have concluded that the maximum number of the electrons in a shell with n quantum number, that is equal to 2n square. That is equal to 2n square. Now, you can solve the numerical also. Find the value of or you can say find the number of electrons in second shell. By 2n square rule, what will be the result? 2n square, 2 multiplied by second shell. N is the number of the shell, square. So what will be the result? 8 electrons. Here we can find in another way that the number of the electrons, they are 8. Now you take n, that is equal to 2. Okay? Here we are taking n is equal to, then L, value of L, then value of M, and then value of S or MS. You can write that. For this, L is 0 and 1, M, that is 0, okay? And here this, for 1, it is -1, 0, +1, okay? S, what will be the value of S? Here 2 electrons, they will be here, and in this 3 orbitals in the subshell. So how many electrons? 2, 4, 5, 6, 7, 8. Again 8 electrons. So this is another way of finding the electrons if you know the value of n. Okay? So one simple way is 2n square rule, and another method, this is very important, you should know this also, how to calculate, and such type of the questions are generally asked. You can solve the number of the electrons in the 4th shell. So there, how many electrons? You will solve it, this numerical on your own. Here I will tell you only the number of the electrons, so they will come out to be 32. Okay? How? 4, 16, 4 4s are is square of this. Okay? 16, 16 into 2, 32 electrons. Now you can write this like in terms of N, L, M, and S. They will again come out to be 32. So this is Pauli Exclusion Principle. In the next video, I will discuss the Hund's rule. That is again very important for filling of electrons in the orbital. Till then, thank you very much.